In order to use matrices to help us solve systems of equations, we have to talk about something called row echelon form. That simply means I'm going to have ones on the diagonal of my augmented matrix and zeros below those. So here I've got a matrix, I've got ones down the diagonal and zeros below those. I don't really care about what's above them. And if this is x, y, z, this vertical line represents our equals and this is our number, this would translate into this set of equations right here. Okay, now x minus 2y plus 4z equals 5. I can't really do much with that. Y plus 3z equals 7. Okay, that's nice. But this one says z equals 6. Why is that good? Because now I can take that and back substitute into this second equation, and that's going to allow me to solve for y. Then I can take the 6 and the negative 11 and substitute both of those into the top equation and solve for the x. Okay, so that's called Gaussian elimination, an algebraic method where we back substitute to get our answers. Now the question is, how do I get it into that nice row echelon form? Well, we have possibilities here. We can interchange two rows. That won't mess up our solution. We can multiply every entry in a row by a non-zero constant. That's not going to change my solution. And we can add a non-zero multiple of one row to another. Okay, so let me show you how that works with a set of two. Here's my system of equations. I'm going to take that and transform it into an augmented matrix by just reading off the coefficients here. Now our goal is to have ones on these diagonals and a 0 down here where the 3 is. You always start in the upper left-hand corner and get your 1 and then your 0 below and then your 1 over here. Okay? So you start at the top and kind of make this L shape. So to get this to be a 1, I can't subtract something that was not one of my operations, but I can multiply it by something. So if I multiply this by 1/2, really you always just multiply by the reciprocal there, it will turn it into a 1. So if I multiply this, I have to multiply everything in row 1, so I denote that as 1/2 R1 to show how I went from one matrix to the other. That top row is now 1, 1/2, and 1/2. And the bottom row we didn't change. We now need to get a 0 below that 1. And I can't multiply by 0, that would eliminate it, mess everything up. So I need to add something to it. I need to add a -3. So I'm going to get that by taking this top row and multiplying it by -3 every single entry, and then adding those results here to the second equation. So I've denoted that -3 times row 1 gets added to row 2, and we replace row 2. I put some scratch work here to show what I'm doing. -3 times 1 would be -3. -3 times the 1/2, -3 halves. -3 times 1/2, -3 halves. So these are the things we're going to add, and we get our 0 at the first entry. A 2 minus 3 halves, well, you can do it by in your head, or you can do it with your calculator. If I do it with a calculator, 2 minus 3 divided by 2, and it's going to return a decimal, but I can turn that into a fraction. Okay, and I get 1/2. So use your calculator or do it in your head, doesn't matter. Same thing here, -2 minus 3 halves is going to get us a -7 halves. We're almost done. So now I need to get a 1 here. How am I going to do that? Well, to get the 1, you multiply by the reciprocal. The reciprocal is a +2. So multiply the second row by 2, and we get this nice 0, 1, -7. Now translate both of those into equations. X, y, so 1/2 y, equals 1/2, and the bottom one is y equals -7, and then you can substitute that -7 up into this top equation and find x is going to be 4.